Welcome back to the second part of our meeting. I hope you all enjoyed the lunch and you enjoyed driving the trucks outside. This afternoon we have a very tight program. We have blocks of every time 20 minutes. So I ask all speakers to really look at the clock and to keep your pace so that we keep on in the program timing. And the block number 1 has 4 subjects. We will start with the aerodynamics, followed by automotive Ethernet communication, and then a very important topic, trailer to train. And I'm very happy that Eric Lambert from CFL is with us because he is on stage to explain this new concept. And then we are going to show the testing, validation and assessment as already Gert-Jan indicated this morning. To introduce you the people who are going to speak in this first topic, the aerodynamic features for the complete vehicle. Please come on stage. It's Elofsson from Scania, who is the Senior Technical Manager and a specialist on aerodynamics. Roy Veldhuizen from the ZF Group, who is also aerodynamic expert and responsible for all the flaps on the trucks we saw this morning. And then Jaap van Muijden from NLR, who is the Senior Scientist also on aerodynamics. Please welcome and good, stage is yours.
Thank you, and good afternoon. So we will explain the work that we have performed and the results that we have achieved from the work package on aerodynamics within Aeroflex. The purpose of our work was to drive the development of next generation of aerodynamic products or innovations, and of course with the purpose to reduce CO2 emissions of long-haulage transports. We have used different tools in our work in 3 different categories. We used Computational Fluid Dynamics or CFD simulations to develop the innovations and develop the concepts that we studied, and also to quantify their performance. And then in order to validate the CFD simulations, we made use of scale model wind tunnel testing. And then finally, which you have seen during this morning, is that we have also built full-scale vehicles to demonstrate the innovations. We perform different typical tasks within each of these different parts. For CFD, of course, we prepared a set of baseline models, including a 500 millimeter extended front end, which you will see in some of the simulations here, and on the scale model as well. We performed, of course, the simulations, and then with the standard post-processing, and also we spent some time on preparing animations and renderings so that we could share the results with you in a good way. And then in the wind tunnel investigations, then we designed a scale model, a 1-to-3 scale model that those of you who are present can see on the side in this hall. We instrumented that vehicle, and then we performed 2 sets of wind tunnel tests. And then finally, we prepared a demonstrator, and there's a lot of work behind that, of course. They started with the design of active and passive aerodynamic devices. Active devices being parts that will change its shape or change its position to improve aerodynamics depending on the conditions. And then, of course, at the end, everything was installed, all the innovations were installed, and we had to spend some time on troubleshooting as well. Early in the project, in the beginning of the project, we defined the targets that we wanted to reach during this project. We defined them for 3 different vehicle categories: a tractor semi-trailer, where we set up the target to reduce the aerodynamic drag by 25%. The DMS1 combination with a drag reduction target of 17%, and then DMS, but with a final detailed truck geometry to achieve a drag reduction of 15%. The definition of the vehicles and how they are compared can be seen to the right on this image. All of the reference vehicles, they have a trailer with trailer side skirts, and then they have a detailed chassis and a generic cab. The innovations or the optimized versions, for the two first KPIs, they have an extended front end, and then for the real demonstrator, it's of course the fully detailed track geometry without the extended front end. If you look at the results at the bottom left in this screen, then you can see that we, depending on how many innovations we included in the models, we gained a drag reduction of more than 40% for the tractor semi-trailer, and the corresponding number for the EMS1, when compared to the reference, that was approximately 40% or higher, or 40% for a realistic combination. And if we change to the demonstrator, then in a similar fashion, we have defined different scenarios where we have a high potential and then a moderate potential, perhaps that comes at a lower cost. And then we decided to opt for a final version that was closer to the initial high potential, but then when we modified it to be really feasible, we ended up with a drag reduction improvement of 29%, as measured in, or as found out in CFD when compared to the reference. When we defined the concepts, or when we developed the innovations, we used different principles for finding the shape of those. The first principle then is to seal the vehicle. Any gaps, either on the vehicle or between the vehicle and the ground, we try to seal them. For instance, with the side skirt extensions that you can see. We also use the second principle to cover large gaps, preventing the air from flowing underneath or flowing between the vehicle units. And for those purposes, we use the side skirts of different shapes and different positions, and we also use the paneling underneath the vehicle. And then we also use the diffuser and the gap reducers, as well as the boat tail, to guide or orient the flow in a suitable way to achieve a low drag on the vehicle. We have also tested flow control that was applied to the boat tail at the end of the vehicle, and also to the gap reducer in between the vehicle units. And you have seen now when I'm presenting that that's the action of the gap reducer. Just to give you a feeling for what it could look like when we apply the innovations. The bottom vehicle then has the standard 4-meter height, and then on top you can see what happens when we reduce the height of the vehicle. And if you look at the area behind the truck and semi-trailer, then you can see that the area with disturbed flow is significantly lower when you have the reduced roof height. And with that, I hand over to Jaap to continue this presentation.
Okay, well, there were a lot of partners involved, and we needed to simulate all the concepts that we wanted to test. But before doing that, we wanted to harmonize our efforts and to make sure that the approaches of different partners give as good as possible the same results. So we started out with a baseline model, did meshing, exchanged information about the meshing, and then performed the simulations just to identify if we were all more or less giving the same results. So what you see in the picture on the right, on the left-hand side, is the drag contribution along the vehicle length. And you see the differences that several partners came up with, even after harmonization efforts for the meshing and for the settings of the flow solver. And that is also shown in the delta CD of the drag of the truck with or without a boat tail. So there is still some differences involved there, and that relates to the turbulence model, for example, and the specific items of the CFD. On the right-hand side, you see the front on top and the rear on the bottom side of the truck, where the pressure distribution is shown. I'm sorry that we did not have exactly the same color scale from each partner, but the results on the front show basically the same pressure distribution, and on the rear side where the vortex shedding takes place, it's quite more difficult, and you get a lot of details, influences from, for example, turbulence modeling. Anyhow, we had this massive amount of concepts, and we started out with doing simulations, and those concepts were ordered in the groups of active and passive geometry, and the group of active and passive flow control devices. And these were distributed over partners, and the partners simulated the effect of those concepts on the drag of the overall tractor-trailer configuration. And what you see here in the figure is basically the result. And you see the drag reduction or the drag increase in bad cases of all the concepts. You can immediately identify the most promising concepts because they show a large drag reduction. And I need to tell you that the blue ones are based on the tractor semi-trailer configuration, and the orange ones were the same concepts, but then put on an EMS configuration. And so that explains the results of the impact of those concepts. Well, having a prioritization of all these concepts in terms of drag reduction, we wanted to make sure that there was no influence on the priorities based on all the different flow solvers applied by different partners. So in the end, we came up with confirmation simulations performed by one partner with the same model, with the same meshing approach, just to make sure that we have no false scenarios in our simulations. So this basically, these let's say drag reduction show good agreement in trends and magnitudes, and between the initial and the confirmed ones. And that gave us some good, let's say, some good feeling to identify the ones that we also wanted to put on the Windtunnel model. Now, all of these calculations, also on the previous slide, we are talking here about, in the initial phase, 120 simulations, and in the confirmation phase, more than 100 simulations. So that was quite a big effort. But then we turned over to the Windtunnel testing. We wanted to validate all the concepts, see if the drag reduction makes sense, and that we could establish that also in a test. So what has been done is a Windtunnel model has been identified, has been defined, scale 1 to 3, and it has been manufactured at NLR, and you can see the result over there. It's quite a massive model, and it has been tested at the FCA Windtunnel in Turin in Italy. That's shown on the picture on the right, where you see the scale of the model in relation to the wind tunnel. The model is basically a frame-based model with plates attached to it, and on the model we could adjust all the concepts in the right place. Well, then the testing itself, what we ended up with was a massive amount of validation data comprising force data, surface pressures, and flow field data, where flow field data were obtained with either 5-hole probes or with PIV, the particle image velocimetry approach, and that uses a laser. As you can see in the picture, the green sheet is the laser sheet, which measures the velocity of particles flowing along. So we have this massive set of data, and that we can use that for follow-on projects or for, well, let's say, industrial developments of the concepts that we have. Now, in order to show how the CFD related to the earlier simulations, we have put a table here with drag results at 0 and 5 degrees angle of side slip. And the wind tunnel model is showing values pretty close to the 1 to 3 scale CFD as well. And the increment from 0 to 5 degrees is very well represented. So the predictions that we made with the simulations were quite all right. Now then there is the issue of having this scale results to the full scale. And so we did that with CFD initially. And that reduces the drag values, the absolute drag values. But we also saw a slight increase of the delta CD from 0 to 5 degrees. And with that, over to Roy.
Thank you. Yeah, so now we did these simulations and also wind tunnel experiments, but then of course we wanted to take the next step, take it out of the realm of concepts and ideas and really put these things to the test. So let's see if we can, as we said it, for the goal for the demonstrator is to demonstrate that these promising aerodynamic concepts can be developed into real life prototypes. And I've underlined some parts because I think the first part is that we want to demonstrate, so really show that these products can be turned into real-life products as, let's say, a first step towards industrialization. And of course, we don't want to do that for every concept. We want to do that for only the most promising. So we made an assessment, not only based on the results, the aerodynamic results from the wind tunnel and the CFD, but also based on applicability, feasibility, and technology readiness level. So it needs to fit to the vehicle. It needs to be it needs to fit in the timeline of the developments that we're doing, and of course, it needs to be feasible. You need to be able to make it and fit it to this actual vehicle. So we took these 14 aerodynamic concepts, and then we developed them into real-life products, or real-life prototypes. So we adapted them for manufacturability, how to install them, how to make a real product out of this. And then basically in an attempt to really show that these are not ideas only, they are really concepts that can be fitted to vehicles and they can really lead to short-term advantages. And an example that I have is the diffuser, which is at the back. I think I should be able to see it. I guess it's not working. You can see it here in this arrow. So we start with the analysis. So we look at the flow fields and simulations and see what is the area that we can tackle. And then as we go throughout this project, we really went to concepts. How can we make this into a real product? Really go to a real life product. So really with bolts and nuts and how to make it. And finally, in the lower right picture, you see it's really installed on the vehicle. So that's basically what we try to do in this phase, is really go from the left top to the right bottom to show that these are not just concepts or, let's say, ideas or dreams. These are things that we can really turn into real products. We didn't only do this for the diffuser that I showed, but there was a whole suite of developments that we did. So here you can see a picture which shows that all the innovations and with them the relative contributions. So how much drag do they give? You can see that the adjustable air deflector, the adaptable box and the trailer shape together, they can lower the height of the vehicle and then reduce the drag. And I think what's special in our case is that these are not individual devices. So we made a system, let's say an ecosystem, that really collaborates. That says, okay, look, I'm going to lower my roof, therefore all you guys, you need to adjust as well, such that we can really reduce the size and go to an optimal shape. Next to that, we have a gap reducer and the bow tail, which is basically devices, let's say, that are adjustable. So you can actually use the same device as a bow tail or as a gap reducer, which means that if this vehicle is driving by itself without the trailer, it can change its shape and then work as a bow tail. So it's really flexible, adaptable to the mission, and it's trying to optimize to every given situation. Furthermore, at the bottom, we have some devices which help to cover the body, as Per mentioned, and also try to cover any surfaces that give a lot of drag, such as the wheels and underbody, dolly side skirts and active side skirts. Basically, what they try to do is convert this vehicle into a closed shape, which is more aerodynamic and thus provides less drag. I think all of those suites together, all of those innovations, led to a drag reduction of 21%. Compared to a state-of-the-art vehicle combination. So that's a vehicle that's already aerodynamic, let's say as it came out of Transformers with a bow tail and a skirt, But still, with these innovations, we've managed to reduce the drag by 21% by using all these aerodynamic innovations. Then I would like to give the word back to Per for the final conclusion.
So just summarizing what we've been presenting today, though. So we defined and designed a lot of passive and active aerodynamic concepts. We selected a few of them and we developed them further and installed them on the demonstrator. And we have achieved significant drag reductions when doing this. On the KPIs definitions, then it's ranging from more than 40% to 29% for the demonstrator. And as Roy just said, when looking only at the detailed demonstrator, looking at what we have innovated now, we can see at least 21% drag reduction from CFD. With that, I would like to thank you for your attention.
Very much, Per. Thank you very much, Jaap. Thank you very much, Roy. I can allow one question out of the group. If there is any question, then you have now the chance before we move on to the next subject. Who dares, who has a question? Question, Simon. Microphone is coming.
Sorry, it's a very technical question.
Hang on, microphone, because of the people home, they should hear what you have to say. Yep.
Oh, thank you. I was just wondering about the drag sensitivity to yaw with the increasing number of vehicles or trailers. Do you see problems when you go to EMS2, etc., or increasing losses, let's say that?
Of course, if you compare a short vehicle with a long vehicle, then they have different yaw polars. The drag increases differently, but I don't see it as a problem. It's just that you have to use the correct polar when evaluating the performance. So not a problem, but use the correct definition when looking at performance.
Okay, thank you very much. Then I would like to propose to go to the next topic. First of all, thank you all three. It was a good presentation and interesting to see all these innovations. I would like to welcome now Andelko Glavinic, who is within the ZF group, the development engineer, and who has developed the automotive internet communication.
Thank you very much.
I'm excited to hear.
Okay. Hello and welcome everybody here at the ZF test track. I'm honored to present you what our part has been in this project, and we have taken care about the communication between the vehicles of each components and what is promising to have in the near future or in the next years. So next slide. So our objectives was first, where were we coming from? So we have for 20 years right now the ISO 11992, which is very common within Europe, and it combines up to 5 trailers within a truck combination. And we found out, or we think that regarding the automotive, automated driving requirements, where cameras are involved and everything else, that this ISO CAN is no more sufficient. Yeah, so we think we should take care, or we should rethink how can the communication between trucks and trailers can be done for the next years. And our challenges was, of course, we want to have a fast connections, yeah, regarding time-sensitive applications. We want to have it flexible for maybe more than 5 trailers when you're looking at Australia and the road trains. And we want to have it reliable and even extendable for future technologies. And our use case was concentrating on the electric engines here in our EMS1 and for the aeroload vehicle. And we think it does not make sense to have additional plugs. Yeah, we already have the 7638, we have the 12091 plugs, and the drivers do not want another plug in it. So we rethink that, we say the new technology has to force no more plugs in this case, and of course legacy support, that we can combine old truck and trailers with newer ones who have these technologies. And by checking the market, we saw that the Automotive Ethernet technology, which is used in passenger cars, which is coming up from the Open Alliance Broad Reach, could be also used on the ISO CAN wires. Yeah, so we have in the 7638, we have 2 wires for CAN. So why not reusing them and making 100-bit instead of 125 kilobaud? And for this, we have built a prototype where we use our existing, where is the marker? Okay, where we used our existing router repeater, which we have in the market, put additionally an Automotive Ethernet switch on it, and made a prototype out of it, which means that we can switch between CAN and Automotive Ethernet just by detecting which car we have in front of us. So if both vehicles are capable to talk Automotive Ethernet, we can switch to it. And of course, a new communication protocol draft has to be evolved because the old one could not be reused because we have more data to transfer. And furthermore, we have tunneled the existent ISO CAN messages with this prototype. So what are the results? We have found out that, surprisingly, for 5,000 kilometers, which the vehicles have driven, we have no malfunctions. So this was running very reliable. We have the full bandwidth. And the switching between CAN and Automotive Ethernet was always successfully. Meanwhile, the project, we have done further investigation and also with the VDA FAT project that's using this kind of technology on the existing ISO CAN does not fulfill the EMC requirements. So one output of this is that this cannot be used on the existing plugs and cables. So we think much further and say, why not taking the next step and creating a totally new plug which will be introduced into the market and which will replace, maybe in near future, maybe in far future, the existing ones. And we are swapping from 100 megabit per second to 1 gigabit per second, beginning on 40 meters, which we also created an ISO standardization new work proposal where we want to bring this into a standardization and therefore in the market. Any questions? Thank you.
Thank you very much, Andelko. I allow one question out of the whole. Has somebody a question? Then not. Then I want to thank you. And yeah, it's a very interesting topic. I believe the only way to get communication on board in a truck combination. Thank you. Good. So we switch to the train. Let's take the train. As said, we will have on the stage Eric Lambert from CFL Multimodal. I believe maybe the biggest terminal where it is about combined transport. Ton Bertens from Van Eck Trailer, because these two gentlemen have really worked very hard to get in our project a sub-project which we have called Trailer to Train, really to look at how can we promote combined transport. And we will start with a little film and then the two of you
Here you see the trailer going into the wagon with the crane system. The trailer we fitted for the crane making new pockets on it. I will explain that later. And here you will see the trailer going on the modular system. So this is a horizontal way of moving the trailer on the train, and before you saw a vertical system. So here is the trailer positioned in the first phase. and then it will turn in the driving direction. Yeah, we brought in the trailers from the Transformers project, the Smith Cargobull trailer and the Van Eck trailer. And we got a question, can we also go in the multimodal segment with these trailers? And for that, we had to optimize this aerodynamic trailer with all those aerodynamic features to fit on the train. But also we got the challenge from, can also these trailers be made that they will fit in an EMS2 vehicle? So being in an EMS2 vehicle, it's also important for the multimodality that trailers like this can go in an EMS2, but also still are fit for the intermodal highway. So what we did, the trailer from Van Eck with all those aerodynamic features, we have to make these pockets in it. So then it was a real challenge because the trailer was already built. And we had to make a complete frame underneath. We took out the holes, brought in the pocket grippers, as we called it. But the system has to be made like that when the grippers moved down, they were kicked out. We made a kind of slide plates that they wouldn't damage the aerodynamic devices. And those grippers were tested. But we also had to change the axles because when the trailers lifted, the axles didn't fall down. And for the EMS2 vehicle, we also have to make a coupling underneath the trailer. So the trailer, a complete frame was built. The underrun protection need to be clappable so that the drawbar from the dolly could fit under that. And also we made a new door closing system to fit for all on the train. So these we realized, and these were tested together with Eric in Bettenburg. And I'll give the word to Eric.
Yes, thank you. Yes, first. Yeah. Yes, thank you. As mentioned, the 2015 directive mentioned clearly that upon these devices, the aerodynamic devices has to remain compatible with the combined transport. So that's what we have here tested. Well, we have then together done this, and for us as CFL, but also I'm the chair of the combined transport group on the UIC, so the Worldwide Association of Railway. It was very important to follow the work together. And here, I'm very proud of the work we have done together from the very beginning. We have then once again proven that the road and the rail can work together. That's very important not to forget. So here you have a picture about the market, but I think you all know so that how the market is divided between the distance that we are driving with the trucks and the tonnage in Europe. So the concept, how to bring the goods on the rail, the concept that we have discussed together was to this one. So is the laser working? No. Okay. So from the left to the right, you have the first step is the pre-carriage, so that we have to pick up the goods together and then to bring somewhere on the railway, on the terminal, to have things lifted, and the transshipment on the rail, and then coming to the next terminal, and from there having the post-carriage for the delivery. That's the easier hard of work. But we can also having this more, what I say, not complicated, but more in accordance with the market expectation. This one. It will say that we could also imagine to have a consolidation point for the goods before using the train. So that's this picture here that you can see, so that the warehouse cargo consolidation, it will say that the trucks will pick up the goods on the different shipper and come to a warehouse where the goods are consolidated. And from there, going to the terminal on using the train. So that we will then, of course, decrease the kilometers on the road, having in one truck the goods for different destinations, and consolidate this in one point using what we name the cross-docking system. So that's what we had then imagined. And then, of course, then we can also then going further with how to work with this. And then you have the different categories of EMS, but I think we will also speak afterward about the different possibility of EMS vehicle. But we can imagine then when using this consolidation point and the train, then we can also have then decrease more and more the kilometers running by the trucks. I will not go too much on this picture. I think everybody knows this because it's a message that we have already heard a lot of time. What I want to say here, what is important when we speak about environmental, about climate issues, we don't have to focus only on the consumption, only on the CO2 emissions. There are a lot of other issues that we have also to tackle. And they are all mentioned here. You have three different pillars. You have the economic issues, environmental issues, and social issues. So I came this morning with a car from Luxembourg. I can say it was really a nightmare. From Cologne until Hanover, the right lane on the highway was one truck after the other one. So 200 kilometers of trucks. It was really a nightmare. We have to work together to have this disappear. That's the aim of the job we have to do here. So here a picture about what we have as a network from Luxembourg. So you mentioned that is a big terminal. Thank you for the advertising. It was not 80, but thank you. So we have a network from Luxembourg, but we are not the only one. We have a lot of networks also offered by our colleagues as Hupac, as Combiverkehr, as Novatrans in France. So you have a lot of network already existing. We don't have to wait having this. They are already there. The trains are there. The connections are there. We have only to explain this to the market, to the shippers. So what we have done as testing, so in Luxembourg, we have the chance that we had the possibility to test different technologies because we are using this in Luxembourg. So 4 different technologies that we have tested. The first is the crane application. So really then taking the trailer with the crane, and that's the film that we have seen. And then we have different technologies that help also to load trailers on the train. Craneable or not craneable. The second is the R2L platform. That's a platform that's on the right, the second on the right. That the trailer is going on the platform. The platform is already on the side of the wagon. And then we have to lift, we lift then the platform with the trailer within the platform into the wagon. Then you have the connection between the trailer and the wagon by using this platform. So then, with this technology, the trailer doesn't have to be craneable. We can also use other trailers. On the left under, that was an ICRASA platform, also a technology existing since several years. This was not so good, I have to say, but also to be clear, the platform that we have in Luxembourg is one of the first, and they are working on improving their platform, so that it was not so, a problem that this platform was not going well, but because they are working on improving. And then the last, on the right, is the Modalor, so that we have also seen on the film. So that's a technology that they are on the platform, so on the terminal, and the wagon is coming in and then the wagon turns on itself. It allows us to load the trailer, and then the wagon closed, and then we can run to the next terminal. So we have this technology in Luxembourg, but also in Calais, in the port of Calais, you have this technology. In Le Boulou, in the frontier, in the border between France and Spain. We have also this technology in France, in Chambéry, also in Torino, in Italy, and last but not least, in Poznan, in Poland. We have also then built this technology that allows us also to load the trailer non-craneable with this technology. I have also, to be clear, to mention the last technology that are coming on the market is Cargo Beamer. Perhaps you know also this name. So Cargo Beamer is a German technology, and also it's the same idea as modular system. So when modular system is turning on itself, the Cargo Beamer technology, the platform is going out of the wagon. So in parallel of the wagon. But that's also the same idea, to have a platform on the side of the wagon and loading this. And then the concept of EMS2 bringing the cargo on the rail, but I already spoke about this. I will not go further. I think it's enough for the test. Thank you for your attention.
Thank you very much, Eric. Ton, one question out of the group. In the back, Steve, the microphone is coming. And then I have another one. Steve.
Thanks. Just really quickly. I mean, very interesting presentation. I mean, I guess I'm partly reacting when we talk about the benefits and the disbenefits of the different modes. Just as a, I guess to lead into my question, I'm a bit concerned when we talk about safety and congestion, when we know actually when we're talking about freight transport, most of the congestion in Europe is in urban areas, 92%. It's not on the long haul. And similarly, safety is so. I guess I'm a bit worried looking forward when we're talking about the last mile. Well, last mile will just make road look less efficient, you know, by all of the metrics we heard about this morning. But just to, I guess, to enlarge the question, because clearly we're not against multimodality. Given that short sea shipping in Europe is carrying currently probably more than 3 times as much ton kilometers as railway, I'm just looking at what, you know, looking at the work you've already done on combined transport, where does short sea shipping fit into this, and how will Aeroflex contribute to that?
I think I can answer. In our use cases we had all in all 32 use cases. There were also a few which were the combination of road and ferry. So we did an analysis, can we enter these semi-trailers also on a ferry? And the answer is yes, because the layout of the trailers is done in that way. Also the side skirts and all the elements we have built in the trucks. So yes, we can also include the ferry transport. So we had some use cases where we really proved this. This was a simulation. I'm honest, but we got the simple chance together with CFL to do this now in a real practice. But I'm sure that looking at the analysis we made, we can do the same with the ferry transport. Talking about your worry about urban logistics, that is true. We, of course, in our project have focused on long-distance transport till the urban environment, where we think that around urban areas you should have hubs or terminals where you put the cargo onto typical trucks which can go solely into city or urban areas. And the question we have to face altogether is that then still the different concept of truck, or do we need another concept of truck? That is something which is of course outside the scope of this project, but you can see at the front-end design we have analyzed, we did also a lot of work to look, can we make the trucks in that way safe, that when they drive into an urban area, they really can see, these are also vulnerable road users, to avoid collisions with them, and that's the topic we will see shortly after this part of the presentation. So yes, the problem you are addressing is also seen within our project, but yeah, we had to look at the scope of the project. I have one question from Rens, and then we go to the next topic, or to Bart, sorry.
Yeah, at the beginning you explained how difficult it was to make the trailer craneable. So how much is the loss of payload by doing so?
Let me say that, but we did more than only the craneability. Yeah? But for only the craneability, it was about 400 kg. Yeah? But also the extra coupling and for the EMS2 was built in, and then in total it would be 800 kilos that we lose for the EMS2 and the craneability. But only the craneability parts were 400 kg, and I think that can be less if you start with a new trailer. If you have a new design, the weight loss won't be that much.
Okay, last question from Bart, and then really you have to go on because the time is running out.
Okay, small remark and a huge compliment. First, the small remark is side skirts on the ferry. I would say it's a challenge. And the second, I want to give a compliment to Eric and CFL, how they embraced the idea, the EMS2, because I've seen in the past that other railway authorities did the opposite. They saw it as a threat, and they embraced the idea, so my compliments to you.
Thank you. Thank you. Thank you.
Okay. Yeah, that was a nice compliment. Thank you very much, Bart. We now go to the next subject, testing, validation, and assessment of the impacts. May I welcome Paul Mentink and Emiel van Eijk, both from TNO Netherlands, and Alex Freja from IDIADA. Alex was responsible for the whole testing and demonstration program at IDIADA, not only the test track, but he managed even to do on a public motorway, and this is, I think, exceptional for the type of trucks we have built, knowing that these trucks were not at all type approved. So I think, I don't know how you did it, but you did it, and it was a formal approval we got, so we did nothing illegal.
Not really.
Not really, yeah? Okay, so, yeah, please, okay. And yeah, success.
Thank you. Okay, well, I have the pleasure to lead Work Package 6, testing, validation, and assessment, with the support of TNO and Han University. Basically, we had the challenge to validate and to demonstrate the improvements of the different technologies on the different vehicles. So to do it, basically we created a test matrix of 12 different vehicles where we included a zero case, that is a standard vehicle running now. We included the results of the transformers, testing again these vehicles. We tested baseline MS1, MS2 vehicles, and finally the demonstrators. Then we determined what we need to measure, what we need to compare. Obviously, we need to ensure that we have a reduction on the fuel consumption. So for this, evaluate this reduction, we determined two different tests, one on the high-speed test track at IDIADA. So we tested a constant speed of 85 kilometers per hour. And then we have selected what we call Fraga route. So this is the route that comes from IDIADA to Fraga and come back. That it's around 242 kilometers and quite hilly. So it looks nice to evaluate the different technologies implemented on the project. Also, we need to determine the improvements on the air drag of the vehicle. So for the reason we started at the beginning of the project 4 years ago with the air drag test that was included on the regulation, European regulation, so it was something quite new. And latest, okay, we have also to verify the dynamic behavior of the vehicle, not just only the dynamic behavior, also the safety after implementing these technologies. So the time constraints, we only focused on the fuel consumption or air drag results of the MS1 and MS2 demonstrators. As I mentioned, we tested on test track, we tested on high-speed thrust. We have seen good results on the MPT vehicle, reduction of -3.5% of fuel consumption. We didn't see this behavior on the constant speed. It doesn't make sense to test in these conditions for a hybrid vehicle. And later, when we compare the improvement on the fuel consumption from aerolot vehicle, we see that reduction of 8% on the test track. So it means we can consider that it's almost a best case for this kind of aerolot implementations. And we have a reduction on the test track of 4.1%. Just then, we tested MS2. We had not a lot of time to do it, but just with a small aerolot modifications, we see an improvement of 2.1% on the fuel consumption. Then we tested also the air drag conditions based on the MPT on the aerolot vehicle, and we see that after performing different tests, aerolot testing, improvement of the vehicle, we had a reduction of 9% on the vehicle. Also, as I mentioned, we tested the dynamic. We like to see this the first time that we had this kind of vehicles at IDIADA. We didn't have any regulation, anything to check for this kind of vehicle. So basically what we did is take the rules of Australia. So it is the performance-based standards from Australia that they have more experience for this kind of vehicles. We defined a type of KPIs indicators for the dynamic tests, so all indicated in the protocol, Australian protocol, and also with the information provided for the Han University that developed a dynamic protocol. We evaluated the dynamic conditions on the vehicle. Initially, we tested the baseline. We seen that the behavior was correct in almost all the tests done. And when we compared with the two demonstrators, we see that we're still inside the same dynamic limits that we indicated. So we can say that we are running in safety conditions. So this is my latest slide. So basically, what are the conclusions of the testing part? We have prepared a robust methodology to test and evaluate the vehicles. We tested for almost 3 years. We did more than 250 tests on the different vehicles. So we have the feeling that we have tested it correctly and we can compare the results. So this is a good point. We have seen the improvements of the different technologies for Work Package 2, Aerobit on Demand, for Work Package 3, Aerolot. And we have also tested and seen that our safety and the dynamic conditions of the vehicles are good. And with all this information, we provided also to TNO for the technical assessment that will be shown in the next slide.
The second part of this presentation is about the impact assessment of the different innovations towards real customer use cases. To start immediately with the key takeaways of the project, which I want to bring over in this short time, is that the innovations all improve fuel efficiency. So the distributed powertrain, together with the air-load innovations and the use of double load floor, contribute to the reduction of energy and by that the application of EMS vehicles to the road. However, the results do, which we will show a little later, highly depend on the cargo type. So what we have seen is that the impact of the innovations is larger for high volume, low mass goods than the other way around, which you might know already. If we look to a cost benefit, so really euro per ton kilometer, we also see that for a particular use case, the innovations pay off. And finally, but not least, is with the developed assessment framework, we are able to simulate any vehicle on any route with any combination of innovation, with any payload. And that allowed us to really stay close to the customer use cases and speeding up the deployment of EMS vehicles and Aeroflex innovations. Just to refresh your mind, we will talk about typically 3 types of vehicles: tractor semi-trailer on the left-hand side, in the middle the EMS1, and on the right-hand side the EMS2 tractor semi-trailer, dolly semi-trailer. Okay, the impact on fuel consumption and efficiency. How did we do it? We have developed a flexible and modular assessment framework which uses a certain amount of inputs, which you can see on the left-hand side, like the origin and destination, the vehicle type, and some specifications on the cargo type. And with the development core micro module modules, we are able to predict fuel consumption in liter per kilometer, liter per ton kilometer, and easily compare different types of vehicles with different types of innovations with each other. And that allowed us to do the work. Of course, you can have this nice framework, but you need to fit and validate. And that's where we have Alex and also the input from the work packages on distributed powertrain and aeroload and double load floor for to give us the right input data to fit and validate the assessment framework. Due to time, I have to direct you to the final deliverable on this to go really through the fit and validation results. Customer use cases. We have had many interviews with real logistic operators and shippers, and we've selected a subset out of many, and in total we took a subset of 8, which in the key message is that they cover different type of logistic operations. They contain up to 14 different vehicle configurations. They are across Europe, have different length and cross different parts of Europe, and by that you have a different hilliness, etc. Also, the intermodal aspect is considered in the sense that we have selected use cases which do have a road rail or a road ferry contribution in them. And by going into detail to one specific customer use case, we will guide you through the process of the type of results you can get out of it.
Yeah, thank you, Paul. So the customer use case that we will introduce now is the one that we call use case 19. It's also been introduced by Gert-Jan this morning. And it includes the transport of automotive parts from Germany to Spain. The parts are transported in gitter boxes, as you can see on the picture. And on the first leg, so the leg to Spain, the vehicle is fully loaded with gitter boxes, so it's a mass-limited transport. On the way back, only the empty gitter boxes are transported back to Germany, and so this is a volume-limited leg. When you look at the route, it's a pretty hilly route. The route crosses the foothills of the Alps and the Pyrenees, but no real mountains are covered, but still there are some considerable elevation changes. And the road types that are crossed in this use case are predominantly on motorways, 95%, and only 5% is on urban or rural roads. We asked the customer what would be his future vehicle if he can choose any vehicle. The first step would be to increase the trailer size to a Eurocombi mega trailer, which is 1.5 meters longer than the trailer that is currently used. The second step is to go even bigger and look at the EMS1 vehicle. And the third step is to look at the EMS2 vehicle, so the 32-meter combination. The results for this use case, everything is compared, is relative to the fuel consumption of the current vehicle, which is a tractor semi-trailer. So when we go up to a slightly bigger trailer, you can take slightly more payload, and the vehicle is a bit heavier, and so the fuel consumption, which you can see in the orange bar, goes up a little bit. But when we correct for the extra payload that can be taken with the vehicle, you see the blue bar, the fuel consumption or the fuel efficiency in liter per ton kilometer. It shows a small saving. When we go up to the heavier combination, so the EMS1 vehicle, the saving increases to over 10.8%. And when we also include the Aeroflex innovations, so the aeroload vehicle and the distributed powertrain, you see that the fuel consumption decreases even more. Although the fuel consumption decrease is about the same for the two innovations, you see that the contribution in liter per ton kilometer is higher for the aeroload, for the aerodynamic devices, because these innovations are a little bit lighter, so they have a smaller penalty on the payload that can be taken in the vehicle. When you look at the combination of both, the clicker, oh wait. The fuel savings in liter per ton kilometer go up to 18% for the EMS1 vehicle. Now, when we go up to the EMS2 vehicle, you see here that it even goes up to almost 27%. And what can be noted here is that the sum of the aero load and the distributed powertrain, the saving is higher than just the two innovations applied separately to the vehicle. So they strengthen each other. Of course, we didn't do this analysis only for one use case. First we go to the volume limited return leg, and here you can see that because there's no penalty on the amount of payload that can be taken, also the savings are a lot higher, going up to 26% for the EMS1 vehicle and 36% for the EMS2 vehicle. Combined, so the both legs combined, it gives a saving of 20% for the EMS1 vehicle and around 30% for the EMS2 vehicle. Here's the slide that I wanted to go to with the results for all the customer use cases. We grouped them. So on the left, you can see 3 customer use cases where the future vehicle is a EMS1 vehicle. And on the right, you can see customer use cases where the future vehicle is an EMS2 vehicle. Again, the orange bars represent the fuel consumption in liter per ton kilometer. The blue bars represent the fuel efficiency in liter per ton kilometer. And the dotted lines show the average. These are the results for the vehicles just going up to a larger vehicle. But when we also add the Aeroflex innovations, you can see that the fuel efficiency increases a lot more. Introducing savings of 15% for the EMS2 vehicle and 20% for the EMS1 vehicle in liter per kilometer, and 7% for the EMS1 vehicle in liter per ton kilometer, and 9% for the EMS2 vehicle. We did not only look at the customer use cases, but also at trans-European corridors.
Yes, so the framework allows to simulate any route through Europe. We thought, okay, what would be the impact of the innovations and these change towards EMS vehicles for main Europe corridors? So we thought, okay, let's use the so-called 10T corridors throughout Europe. For what we have seen so far is not any other European project have translated the developed innovations towards benefits in terms of what would it mean for 10T corridors. So for us, it's rather a unique application. But it also allows you to play around with all kind of inputs which we have, and I will come to that a little later. For those who are not aware of the 10T corridors, it's a trans-European transport network. The key purpose of the 10T policies in Europe is to strengthen the economical and social cohesion between the nations in the European country, and to improve and get rid of the bottlenecks and the hurdles in the different types of transport, so road, rail, inland vessels, marine, the ports and harbors. Since also our time, maybe it's good to mention, in total there are 9 so-called 10T corridors. Our time was limited, though, to take them all. So we took a subset of 2, and they are called the Mediterranean 10T corridor and the Rhine-Alpine corridor. And the results I will show you is for the Rhine-Alpine. Similar kind of conclusions can be drawn for the Mediterranean if we talk about the impact of the innovations. So again, I have to refer you to the final deliverable to have a look at that. Going to the results. Like Emil shown, so in the orange bars we see relative savings in liter per kilometer, and in blue we see the savings in liter per ton kilometer. We have varied the cargo density, so I have low, medium and high cargo densities. I have different types of vehicles, EMS1 and EMS2. All of the results are compared to a standard tractor semi-trailer unit, and for each vehicle configuration, we have applied different innovations. So the left-hand side, that's just going towards an EMS vehicle. Then it's only adding the aeroload innovation to it. Then adding only the distributed powertrain, and then a combination of the two innovations. You might think of why not having the double load floor in. The double load floor would mean an additional benefit on the results we show you here. We not only do this for an EMS1 vehicle, we also do it for an EMS2 vehicle, also with a low cargo density. And you still see that you can gain medium cargo and also weights up to max gross combination weight. So the 40 ton for tractor semi-trailer, 60 ton for an EMS1 and 74 ton for an EMS2 configuration. And you can clearly see that, like was already shown in the customer use cases, that the impact of the innovations is bigger for high volume, low mass transport. You also see that there is a consequent reduction, positive effect of the aeroload and distributed powertrain, and again, there is this strengthening of the effect, and it's mainly caused if you would, for instance, go downhill with a vehicle which has distributed powertrain and aeroload, you have a lower air drag resistance, and by that you have more energy which you can recuperate by the e-drives, which you can use later on. Yes, then quantifying certain impacts. So you see that the EMS1 vehicle can reduce or improve the fuel efficiency in liter per ton kilometer with about 11% on volume limited transports, whereas it will be 7% when it is mass limited. So that's the one on the right hand side. And you have additional gains by the Aeroflex innovations on top. For the EMS2 vehicle, and on absolute levels we talk about that we can go for an EMS2 which goes up to 28% improvement of fuel efficiency towards 35% if you apply the Aeroflex innovation to an EMS2 vehicle. Everything about fuel efficiency, we now go to what does it mean in terms of euros. And that's why we took the use case of the automotive parts as an example, and we calculated the so-called cost benefit, and that is what I want to show you right now. We took 9 different cost aspects into account, mostly familiar to you, and you might know that for a regular truck trailer or tractor semi-trailer, fuel, driver and financing are the most dominant costs typically. All the assumptions taken on the cost aspects, etc., that is simply too much time now to discuss. We can discuss it afterwards. It's also been part of the final deliverable. So like I said, we will use the automotive parts use case presented by Emiel a little earlier. And the cost savings are relative cost savings in euro per ton kilometer again. And you remember also that the use case was having a leg which was mass limited and a leg the way back which was volume limited. And we also separated those two in the cost benefit analysis. So we have a mass limited and a volume limited result. First, I want to show you what the savings are of just applying EMS vehicles to this particular use case. And you can see that EMS1 in the mass limited condition saves about 17% in euro per ton kilometer. And for the volume limited transport, the impact is a little bigger, it's about 21%. EMS2 vehicles range from -28 towards 32%, so they have an additional gain. But now I'm also curious, and you might be as well, what is the contribution of the developed Aeroflex innovations? So you can see that in the mass limited situation, we are more or less cost neutral, and we have a slight penalty on the EMS1 vehicle in terms of cost in case of the mass limited transport. But if you look to the volume limited transport, you see that we have a gain of 24% for EMS1 vehicle with Aeroflex innovations and 36% for EMS2 with Aeroflex innovations. That brings me again to the key takeaways, which I started the presentation with. And I would like to thank you for attending and enjoy the remaining of the final event.
Thank you very much, Alex, Paul and Emil. A lot of work has gone into this, I think, and yeah, time was too short to tell everything, and that's a pity. But as you said, all the assessment values are in the final deliverable, which will be available. I still want to allow 2 questions. Eric, you have a question in the back of the hall.
Eric Dahlberg, Scania. First of all, very nice findings and in efficiency results, and not least fuel efficiency. I have a question related to the first part of this presentation where you mentioned that you calculated the vector values. And the background to my question is that, as you know, EMS vehicles are, let's say, penalized compared to normal long haulage vehicles because they use the same payload in the vector calculation still. There is an upcoming revision of this regulation for next year in which we hope that there will be a change. But how did the EMS vehicles you calculated come out compared to the same vehicle if it was used in long haulage, or other vehicles more optimized for long haulage?
Yes, this is one point that will be also indicated when we talk about the homologation for the die drag and for calculate, so it's some points of improvements. And the vector tool has an option that you can calculate these MS1 vehicles and simulate the impact of the devices. We can provide additional information on how it's done after the meeting with more technical details, if you want.
Don't have an answer as a value, or is it too long, or?
I don't have this.
Okay, okay. So you have to look at it, and then
yes.
Okay. So this can be answered after the meeting because it's not.
I don't have exactly the number.
Okay, so you will come to back then.